So, we will continue with our derivation of that Navier-Stokes equations or the equation of motion, equations of fluid motion. And the equation that we are now deriving, as we mentioned, is known as Navier-Stokes equations. Because both Navier and Stokes, they derived these equations independently. Now, we derived an expression for the deviatoric stress tensor. If you remember, d I j was 2 mu E I j plus, I think we wrote mu 2 d u k d x k delta I j, and this d u k d x k, as you know, is the rate of expansion or dilatation, and in the conventional vector notation can be written as a divergence of the velocity. Okay. With this, the complete stress tensor we wrote sigma I j as minus p delta I j plus 2 mu E I j plus mu 2 divergence of u delta I j. Now, looking to this deviatoric part of the stress tensor, it is the normal component in this deviatoric stress tensor are the remaining part of the normal stresses, from which we have taken out this isotropic part, this minus p, which is the one average of the sum of the diagonal. This we have taken out from sigma I j. So, what remain in the, say, sigma 1 1, sigma 2 2 and sigma 3 3, that is contained in this part d I j. And since sum of the average of the sum is minus p, then the remaining that remains sigma 1 1 minus p, sigma 2 2 minus p, sigma 3 3 minus p. When you sum them, that is 0. That means, the sum of the diagonal elements of d I j is 0. So, this is by definition that d I j is 0. Now, let us see what does it mean. Now, what is d I I? Sum of the three elements, 2 mu E I I plus what will be that? The second term, when you contract, when you make I equal to j, what will that term be? So, you want to think about the three terms separately, say mu 2 d u k d x k delta 1 1 plus mu 2 d u k d x k delta 2 2 plus mu 2 d u k d x k delta 3 3. So, what it will be? Mu 2 du2 dxk into delta 1 1 plus delta 2 2 plus delta 3 3. What is delta 1 1 plus delta 2 2 plus delta 3 3? 3. So, that term becomes 3 mu 2 du k dxk. Du k dxk is same as E k k, we can write as E I I. The second term becomes 3 mu 2 E I I. Okay. And this is equal to 0. By the definition of our diffeotic stress tensor, this is 0, and this gives us mu 2 equal to minus 2 by 3 mu. So, this we have been able to even eliminate second coefficient of viscosity by the coefficient of viscosity itself. So, if we substitute now, then this sigma I j becomes minus p delta I j plus 2 mu into E I j minus 1/3 divergence of u delta I j. Okay. Then this we can now substitute in the equation of motion. The equation of motion, if you remember, was the equation of motion becomes what? By the way, this is, before we write down this equation, this relation that mu to second coefficient of viscosity is minus 2 by 3rd mu, this is usually known as Stokes hypothesis of viscosity. Okay, now equation of motion becomes, look back, rho d u y dt equal to rho f I plus d d x j of sigma I j. So, that we can now write d d x j of minus p delta I j By the way, as you can clearly see that this equation is written in terms of unit volume basis, it is clear. It is conventional to write the equation in terms of mass basis in solid or rigid mechanics, while in fluid mechanics it is conventional to write the equation in terms of unit volume basis. So, in this equation each term in this equation represents some force per unit volume. As you can say, the first term on the right hand side is simply the body force per unit volume, and this entire term, the second term is the surface force per unit volume. The left hand side is of course the inertial force, which contains the local rate of change of momentum plus the convective transport of momentum. The left hand side contains, as you know, that this material derivative is sum of two, a local derivative which is simply the partial derivative with respect to time. So, that gives the local rate of change of momentum, and the remaining three terms u y d u y d x j, sorry, u j d u y d x j, that gives the convective transport of momentum, the way momentum is being convected. Now, looking here, this first term within the bracket d d x j minus p delta I j, we will take it out from this bracket, and what then that term will become? That term can be written as minus d p d x I. d d x j of minus p delta I j is minus d p d x I plus the remaining term d d x j of 2 mu E I j minus 1/3 divergence of u delta I j. This d p d x I is basically the gradient of pressure, d p d x I. Now, see, this coefficient of viscosity is in general a function of pressure and temperature, and not only that, its dependence on pressure is extremely weak. So, that all practical purposes coefficient of viscosity can be thought of as a function of temperature alone. Okay. So, if this coefficient of viscosity as a function of temperature alone, and there are many flow problems in real life or in practical applications, where the temperature variation is really not large or not considerable, temperature variation are really negligible. So, if in that situation this mu can be thought of just a constant. If there is no change in temperature or practically no change in temperature, then mu can be taken as constant. So, you can write that if temperature change is negligible, and then this mu can be taken out of the derivative, and the equation will become where you have replaced that E I j is half of d u y d x j plus d u j d x I. We have replaced E I j by its definition, and that divergence of u once again you have written this form d u k d x k. Now, if the flow is incompressible, we know by conservation of mass or by equation of continuity divergence of u is 0. That means, this second term is 0 there, and this equation becomes so. This is the final form of the Navier-Stokes equation if the flow is incompressible, and this will be taken as the final form of the Navier-Stokes equation when the flow is not incompressible and mu is not constant. Mu cannot be taken, temperature changes are not negligible.
What is the relation between mu and T? The equation.
There are many relations. The most popular relation used is called as Sutherland relation, okay, which is can be expressed as something like this: mu by mu 0 is T by T 0 to the power 3 by 2 into a constant. The constant is usually written as T 0 T plus S by T 0 plus S, where S is again a constant. T 0 is reference temperature and mu 0 is a reference viscosity, a Sutherland relation. But particularly in this course and also the next course on aerodynamics, we will consider mostly incompressible flow. So, this is the equation that we will be using quite often, or even perhaps some simplified form of this equation. In the standard vector notation, this equation you can write as rho in the standard vector notation, and you have to remember this equation always in all form. Now, this is of course a vector equation, means it can be written for 3 components, 3 separate equations. Now, let us summarize at this stage. As far as governing equations of fluid motions are concerned, we now have 2 equations. Of course, one of them is in vector So, basically 4 equations, the continuity equation and these 3 component of the Navier-Stokes equations. So, we have 4 partial differential equations.
How is the mu dropped there? When you do Laplace square u, why is the mu dropped?
Oh, sorry, it is not dropped. it was just oversight and mistake. So, these 4 partial differential equation, of course, the continuity equation or equation of mass conservation is a first order partial differential equation, while this is a second order partial differential equation. The equations are nonlinear, because in both cases this term is present, whether the continuity equation or this Navier-Stokes equation, this term is present, which as you know can be written as d u dt plus u j d u y d x j. So, that term u g d u y d x j, that is nonlinear, the coefficients are themselves unknown functions or the actual variables. So, the equations are nonlinear partial differential equation. Anyway, and these 4 equations, and how many unknown we have here at this stage? We have 3 component of velocity. So, 3 unknown plus pressure and density. So, we have 5 unknown in 4 equations. So, we need one more equation to supplement it, and the easiest equation that perhaps we can think of is the equation of state, which relates any particular state variable in terms of 2 other state variables, and the most often the density or pressure in terms of, say, let us say pressure in terms of density and temperature. But if we use that, immediately we get one more unknown, the temperature. Then we need one more equation. And also at this stage perhaps I should mention something about this pressure again. If we use the equation of state, the thermodynamical equation of state, the common example, the equation of state for a perfect gas, as you know, P equal to rho R T. Now, we have already mentioned that the pressure as defined in thermodynamics as a state variable is not the same the way we have defined the pressure here, which we have taken as simply the average of the sum of the surface or normal surface stresses. The basic difference comes in from here, that in thermodynamics all state properties are defined using a thermal and mechanical equilibrium, and of course, in a fluid motion they are not exactly in thermal and mechanical equilibrium. So, the quantities which are defined as state variable in equilibrium thermodynamics is likely to have certain differences when they are not exactly in equilibrium. And without going for any mathematical proof or anything, I will just state that the difference, what is the difference of this pressure with the pressure in defined in thermodynamics or the fluid static pressure. The fluid static pressure is same as the thermodynamical pressure, because when the fluid is at rest, it is also in mechanical or thermal equilibrium, what is assumed in case of thermodynamics. So, the fluid static pressure is same as the thermodynamical pressure or the equilibrium pressure, but pressure in moving fluid, which is 1/3 of the sum of the diagonal terms of the stress tensor, is not the same. The difference in quantitic form will not go for any proof or anything or even derivation, we will just simply state the difference between this thermodynamic or equilibrium pressure we are just the difference between these two pressure is given by this. The derivation is to some extent similar the way we have derived the deviatoric stress tensor, considering isotropic fluid and all those things we did last time. So, in the similar manner this also can be derived, but we will exclude that from here, we will not consider, and the magnitude is given by this, where this is, as you can say, is equal to or very close to the coefficient of viscosity, and divergence of u is the rate of expansion or dilatation. So, you see, if the fluid is incompressible or if the flow is incompressible, then divergence of u is 0 and the difference does not exist. So, in case of incompressible motion, even though the fluid is moving and not in exact thermodynamical and mechanical equilibrium, this difference is 0. That means, both can be taken as the same thing. The pressure in a moving fluid is same as the thermodynamical pressure or the static pressure. However, when the rate of expansion is non-zero, as in case of a compressible flow, there is a difference, but again this quantity being very small, even though rate of expansion is larger, still the difference is very small. However, there are some cases where the rate of expansion approaches very large value, extremely large value, then of course, this is considerable. But in most usual cases where the rate of expansion is not that high, is some average or moderate value, again these are negligible. So, in usual cases we need not consider a difference between these two pressures, and henceforth in all our discussion we do not have to consider that difference. We will take it for granted that whatever pressure we are finding, that is the same as the thermodynamic or equilibrium pressure as well as the pressure in a moving fluid. Now, we will look to something special in this equation. If you look to the Navier-Stokes equation and say for simplicity look to the last term in the case of incompressible flow. Yes, what we said that even in compressible flow that difference is very small if divergence u is not extremely large.
Where does this come from?
Hmm?
Where does this come from? This difference.
See, this is the difference.
How do you get that? Where do you get this formula from?
Oh, acha, this derivation. See, this derivation I wanted to exclude. As I mentioned that this the derivation is similar to the derivation of the deviatoric stress tensor Dij. Assuming that this difference, since this difference is due to the flow or non-uniformity in the flow. So, this difference must be proportional to the velocity gradient, the way we made Dij proportional to velocity gradient, and then again writing another matrix in that tensor form, that P minus P minus this P thermodynamic can be written as say a tensor, velocity gradient tensor proportional to velocity gradient tensor, which can be equated to again B I j k L d u k d x L. The way we made the deviatoric stress tensor d I j equal to A I j k L d u k d x L. Similarly, here also we can write that P minus this P thermodynamic, this quantity is proportional to the velocity gradient tensor, and hence can be written as B I j k L d u k d x L. And again using that isotropic nature, ultimately it can be brought to here. That complete derivation I wanted to exclude, but this is the way. Once again you can try it yourself. Look to this Navier-Stokes equation, let us say for the incompressible case, because that is a little simpler to handle than the other one. Let us write it once again, or in the vector form only, rho du dt equal to rho f minus grad p plus mu each term here it represents a force of per unit volume. Okay. So, the last term which has come, if you remember, is from the non-diagonal term of the deviatoric stress, non-diagonal term of the deviatoric stress or the shear stresses, come from the shear stresses or tangential stresses, which is because of the velocity gradient and coefficient of viscosity. They are usually called as the viscous stresses. And we have already seen that while deriving that expression for deviatoric stress tensor, that they come exclusively from the rate of strain tensor. If there is no rate of strain, then there is no shear stress or viscous stress. This we will now call it viscous stress per unit volume, or viscous force per unit volume. This viscous force per unit volume has come from obviously viscous stresses or the shear stresses, which is completely due to the rate of strain tensor. If there is no rate of strain, then there is no viscous stress. Now, look to this. So, this viscous force per unit volume, we will call it viscous force per unit volume, all term are per unit volume here. Now, using a vector identity, Laplacian, the operator Laplacian can be written as gradient divergence of u minus curl of u. Now, since we are dealing with incompressible flow, this first term is 0, the first term is 0 because divergence of u is 0 for incompressible flow. So, this becomes then minus mu curl of, this curl of u is omega, the vorticity, okay. So, we see that viscous force per unit volume is obtained or given by the curl of vorticity, curl of vorticity. Now, while deriving this equation, we have already seen that this term has come from viscous stresses or the shear stresses, and the shear stress has come only because of strain rate. Rather, we have shown there that the vorticity part has no contribution to the stress. Vorticity does not contribute anything to the stress, to the shear stress. So, vorticity has no contribution towards shear stress, and shear stress is the reason of the viscous force which is given by the vorticity. How is it possible? We have seen correctly, it is not only a pure simply mathematical derivation, it was even physically correct that the rigid body rotational type of motion or the vorticity has no contribution towards the shear stress. The shear stress is given by strain rate alone, and only shear stress is what is giving the viscous force, and then we are seeing that the viscous force is given by the vorticity. So, it cannot give the stress, but it gives the force. How is it possible? Any answer? So, you think that imagine a situation, the flow is irrotational, a flow which is irrotational, there are many such flows which are irrotational, then this viscous force is 0. Even not only irrotational, even if the vorticity is uniform, vorticity is uniform everywhere, then also this is 0. So, is it that whenever the flow is irrotational there are no shear stresses, because viscous force is 0? That of course, we can't say, because we know that vorticity has no contribution towards shear stress, that comes because of the strain rates or particularly the tangential strains. Then where is the problem? Where is this discrepancy? this equation to be looked into, this particular equation is to be looked into just a mathematical relation because of the identity of this vector operator. This is not a cause and effect relation. This is not a cause and effect relation. This is just a mathematical coincidence that the viscous force has become curl of the vorticity, just a mathematical coincidence that the components of viscous forces are obtained from the components of the curl of vorticity vector, and has come because of this vector identity by which Laplacian is expressed as gradient divergence minus curl of curl. So, this will be true that if the flow is, if vorticity is 0 or vorticity is uniform, then the viscous force per unit volume will have 0 magnitude, but the viscous stresses will be non-zero, will may be non-zero, but the viscous stresses will give a total viscous force of 0 magnitude. So, while strain, rate of strain and viscous force are cause and effect, this vorticity and viscous force equality is not cause and effect relationship, it is just a mathematical coincidence, a mathematical relation. Once again, I think we left that discussion in between, that at this stage when we have the conservation law for mass and momentum giving rise to 4 equations in 5 unknown, and to add one more equation, we can fall back upon the equation of state P equal to rho r t. Okay. And then of course, we resolve that difference between the two P, the P in the momentum equation and the pressure in the equation of state. However, so we need one more equation to have, because as we had a sort of one equation, we added equation of state, but when we added equation of state, we added one more variable. So, obviously, we need one more equation. But look to the case of incompressible flow. In incompressible flow, we have already stated that by definition incompressible flows are those flows where density does not change due to pressure, where density does not change due to pressure. In addition, now if we consider that the temperature changes are very small or negligible, that is practically temperature do not change, then density remain constant. Density can change because of pressure and temperature. Incompressible flow means the density does not change because of pressure. So, if temperature is also constant, then density does not change at all, and most often by incompressible flow we take that the density is a constant. So, when density is a constant, now we have only 4 unknown. Density is no longer an unknown, it is a constant. Okay, a constant also can be an unknown, but we will take that constant is known constant. Or even if we want to find that constant, we can consider any one point where other conditions are known, some conditions somewhere must be known. So, from that point we can find the density and that remain constant. So, the density is no longer an unknown for the differential equations. So, we have 4 unknown now, 3 component of velocity and pressure, and we have 4 equations. The equation of state in this case simply becomes rho equal to constant. Okay. So, we can solve these equations with, at least theoretically, that we can solve these 4 equations for the 4 variables, and
So, if the temperature is not constant, why can we take mu as constant? We have not counted mu as unknown.
See, mu is unknown because we will be having some relations, but we are not actually considering it as unknown for the differential equations. That is already supplemented by some equations. If the when the temperature will change, okay, when the temperature will change, we will need one more equation, and not only that, we will need a relationship for mu also. So, this we are considering where mu is constant, the temperature is not changing. So, mu is nearly constant, okay, and incompressible flow. So, density is also constant now. So, this density and viscosity, they all of them have become constant. So, the unknown that we have are the three component of velocity and pressure, and these four partial differential equation, the three component of this equation and the equation of continuity, these four equations together are sufficient, at least mathematically, to solve for these three unknown variables, four unknown variables, three components of velocity and pressure at all points at all time theoretically. However, there are certain other things that must we have, like we must have a specified boundary conditions, we must have some specified initial conditions. Those are requirement of solving any differential equation, even ordinary or partial, whatever it is, that you must have some boundary conditions, you must have some initial conditions as well. So, provided we have all those, the boundary conditions and initial conditions, then these four equations are sufficient to solve. However, unfortunately, the equations as you can see are quite old, 200-300 years old, the equations. Those Navier and Stokes, they were in those time. Unfortunately, till date, for any given general boundary condition or initial conditions, no solution has been found by mathematical means. Only some simple cases, the equation can be solved, and we will discuss such simple cases. However, for complete solutions, ultimately one has to fall back upon numerical methods. But anyway, that is quite far away as yet. We will go to that numerical solution of these equations quite late in your curriculum. But before that, we will try how to solve or how to get the solution. Instead of solving this equation completely, how to get the solution, but that we gradually build up. Okay, now, one or few more words about the case when the flow is not incompressible. Then, as we mentioned, that this will be the strategy, that okay, these four equations with 5 unknowns, we can bring in one more equation by the equation of state, usually pressure expressed as a function of density and temperature from thermodynamics, and we can have the difference between these two pressure, the pressure in the momentum equation and the pressure in that equation of state. We can even neglect them because the difference is small. However, introducing that equation, we have introduced one more unknown, the temperature or maybe internal energy. Sometime pressure is expressed in the form of, or internal energy is a preferred variable than temperature, and one more equation is needed. However, we have one more conservation equation, which we have not discussed as yet, the conservation of energy. Of course, a scalar equation, and assuming that that is not giving any further unknown, further field variable, that will complete the set of equations. Of course, in that case, temperature being a variable, we have to have certain relation for expressing the coefficient of viscosity and anything else if we bring in, that also must be expressed in as a function. See, when there are partial differential equation, it is customary to consider them to be the equation and any other equations as not as equations, they are just relations. So, that if we have a viscosity relation, as an example, that Sutherland relation we are talking about, mu by mu 0 equal to say T by T 0 to the power 3 by T into T plus S by T 0 plus S. This mu 0 and T 0 is at reference temperature and the viscosity at that reference temperature. This S is a constant usually taken as 110 point some K. This temperature is in Kelvin. So, this is called Sutherland relation. So, this type of relation are not called an equation. By equation, then we will be meaning only partial differential equation.